finally, I'm going to use, well, a little bit of the Arnold proof on PSS moduli space motivation to really finally rigorously, introduce polyfold theory. But again, I'm going to start with the big picture. And I hope to very rigorously get to the one sort of generating germ, which is scale calculus, and there will be pretty much just one other generating germ, hopefully on Wednesday, that runs under the sort of buzzword of splicings. And then with respect to these two, we're going to have to talk a little bit about what Fredholm theory is. But pretty much once you have these two ideas, the rest, well, is an exercise, non-trivial exercise, which is performed on the abstract level completely. That's all published. So the abstract theory, I think, is fairly complete. And there's work in progress. Well, the Gromov-Witten story is also essentially complete. And what's missing is the symplectic field theory application that I need to prove the Arnold conjecture. And that's also why I'm not actually going to talk about that example, because there's a couple more pesky sort of setup things. So I'm going to go back to this example of Gromov-Witten, which I think illustrates the ideas mostly. Also, if you want to look at ideas, there's several surveys by Hofer, and I, with a couple of other polyfold experts, have, well, we wrote what started as a dummy's guide to polyfolds, and then it became polyfolds at a glance, and then it became long, so now it's polyfolds at first and second look. And it's still not submitted, so if you find any hiccups or things that you don't quite understand in that survey, definitely let me know. So, okay. So, what is a, let's say I was trying to prove, a step in the Arnold conjecture proof using, the SFT polyfold setup. Then what I would need is I need to write down my compact moduli spaces as usual. And I need to somehow give you a construction of a bundle and a Fredholm section so that the moduli space is given by the representation, right? So the topological representation, as usual, is the zero set in the objects, more the morphisms. And they're now going to sort of be rigorous in terms of some language that has polyfold in it and polyfold Fredholm. And in that language, there is a rigorous theorem that I get pretty much by copying my wish list and putting Hofer-Wysotsky-Zehnder in front of it. So, whatever this notion of bundles is, there will be transverse multi-sections so that the zero sets of the transverse ones cut out weighted branched manifolds that are unique up to cobordism. If I had transversality, I don't need to perturb. If I'm given a transverse thing on the boundary, I can extend, keeping the transverse thing on the boundary fixed. And since our boundaries are often products, products of transverse things are transverse. So that's a whole package deal that, exists if you're in, say, smooth sections of finite dimensional bundles. You can imagine proving all of these things. And this whole polyfold language is made so that, you know, that theorem pretty much directly extends. So, actually, this is sort of funny. So you could number these HWZ 1, 2, 3, you know, up to 10 or 11. In my days, HWZ 1, 2, 3 was about holomorphic curve foliations in non-compact manifolds. So there's a whole, you know, sort of sequence of Hofer-Wysotsky-Zehnder collaborations that happened before polyfolds that, you know, when you talk to older people, you get them very confused if you talk about HWZ2, because there's now sort of two parallel lines, which really, you know, in some sense, the older work was sort of the analytic background for symplectic field theory. And now they're doing this whole work to, you know, regularize all of those spaces that they made sort of the, you know, elliptic theory and compactness theory for first. Right. So the thing that I'm gonna cheat around, and we'll need to see how far we get with respect to uniqueness, is right here. You give yourself a moduli space, you describe it. There's certainly choices involved. So the question is going to be, what happens if I make different choices? So there's certainly a choice of possibly different sort of ambient spaces and hence different bundles in the different section. There's usually also a choice of complex structures involved, or almost complex structures, and yeah, changing them should yield somehow equivalent sections in some sense. And then hopefully that equivalence allows me to go back into that theorem, you know, and you know, the hope really is that that theorem is already general enough that the equivalence gets me into a setting within these polyfold sections that then again is going to tell me that somehow the regularizations are essentially unique. We'll see a little bit of that. But I think, well, there's some degree of generality in which I think that's not part of the abstract language yet, but we can start dreaming. So mainly I want to, well, I'm going to sort of do the dual thing. I'm going to sort of start with the actual construction and in the process tell you what the axioms for a polyfold bundle are. So, and I want to at least sort of, I'm not going to do it in this example, but I want to claim things for the SFT example that's actually relevant for the Arnold conjecture. So my goal is to state a conjecture here that actually will be proven by HWZ, and that also, once it's true, will imply the Arnold conjecture. So I need to somehow say how I'm cutting out these SFT compactifications of these nice moduli spaces that I had, right? I had these sort of graphs of curves, and for the PSS in C times M, sort of graph J's, finite energy, fixed asymptotics at Hamiltonian orbits, and then they needed to get compactified somehow. Right. So here that sits, I guess, in, I want to write this as n bar just plus minus, which is, however, a union over different periodic orbits. Right? So there's different connected components depending on what that last gamma is. And what else? Right, the other structure. Yeah, this C here has a marked point 0, And that somehow needs to survive in the compactification that's here. So it'll take a while until we actually can talk about that. We'll mostly talk about this sort of subset which we think might be dense, but in general for holomorphic curves might not be dense. So I want that cut out simply from an ambient polyfold. So there's going to be a polyfold for PSS and for SSP. There's also going to be a polyfold for each of these guys. Right? So the neck stretching one and the neck length equal to 0, 1. So this will be an n bar 0, this will be an n bar stretch. Now that's my n bar subscript star here, and so for each one of them I should have a polyfold. And let's see, do I already? I think I want to claim already what my stretching. No, I don't want to claim what the stretching thing looks like already. It just kind of makes sense to decompose the PSS and SSP things also according to limits of Hamiltonian orbits. So. And then over each one of those there should be polyfold bundles. And Fredholm sections, or polyfold Fredholm sections, in each one of them, from the base to the fiber. So that. So certainly I want to cut out the compactified moduli spaces, but I need a little bit more. The little bit more I need in order to be able to couple these things with the Morse moduli spaces via evaluation maps. So I like my evaluation maps. Well, there's one's at 0 and one's at infinity from whatever B I'm on to M. I would like that to be appropriately smooth in a polyfold context. So let's see, where's the 0 was here. Here I have a 0 and an infinity. Oops, that's actually, those are the wrong, is that the wrong place? Yeah, that's the wrong place. I'm actually right, I explained the evaluation maps as intersections of the graph or of the image with the sort of sub-manifold 0 times n. So 0 and infinity kind of actually now lie in the target. So you can still think of these as marked points here. And here also. And the one other thing that we were looking at was this family here for R between 0 and infinity. I wanted some boundary from that. This here as a polyfold we expect to actually not have boundary. This will have boundary from the fluid breaking, but I don't care about that. So at least I think in my proofs that didn't appear. All I need is to know what the boundary of my stretching polyfold is, namely length 0 and length infinity. And length infinity is the breaking into PSS and SSP. And that's what I want, this split thing, so I can sort of take the fiber product over periodic orbits. And if I'm really anal, I'd probably like this to be a cobordism, so there's, we're not going to talk about orientations, but we want Just like the interval from 0 to infinity, one of these should come with a minus sign. So I believe that if that is proven, then what I've explained proves the Arnold conjecture. So that's sort of an exercise in trying to sort of actually put all the nice properties of holomorphic curve moduli spaces into one black box. So that then you can just sort of apply black box regularization theorems to whatever abstract section there is. And this is probably the last that we're seeing of these pretty wild moduli spaces. So, now I did want to say one more thing. So this is sort of announced as result. So I have a conjecture that somehow I can't really precisely state, but my conjecture is that somehow this data here is sort of uniquely determined by certain things that I can say now without having to say what a polyfold is. And that's what I kind of already said before. So, all these sections, bundles, and polyfolds should be up to some appropriate notion of equivalence, uniquely determined by, well, right, so we had our moduli spaces were spaces like this, except there was a Cauchy-Riemann equation. And so I'm just going to drop the Cauchy-Riemann equation and just look at the smooth maps. And so those should be dense. I keep saying that they might not be dense in the holomorphic curves, but within the flattened spaces, I could ask the smooth ones to be dense. And now here there's a realization of the polyfold, meaning really what's going on here is I have an object space, right, which are the sort of charts of a Banach manifold, and I have transition maps of my Banach manifold. That's the morphisms. So that's what you should think when I write this whole sort of subset. So if these are topological spaces and these are sort of given by continuous maps, then this quotient space has a topology, and I can think about smooth non-nodal maps being dense. And with that, I can, so that's the, oopsla. Oh yeah. Yeah, there's a fun game here that apparently you can play. So you can, oh no, now I can't. You can turn these and it looks really weird, but, so, and once I have these polyfolds, I can actually make a new polyfold simply by making a product. So, right, for finite stretching parameter, the maps will have to be JR holomorphic, but they're still just smooth maps. So I can take actually the same ambient polyfold, and so just take a product with that interval. So, whatever reasonable notion of polyfold there is, if you take a Cartesian product with a manifold, that better be a polyfold again. But then we need to add the stretching parameter infinity, so we're just going to start with a disjoint union of these oops, not stretch. It's the Cartesian product over the periodic orbits. And then I somehow need to topologize this. And that's where, this is very similar to, topologizing broken or nodal curves within the space of all curves. So there you can use a pre-gluing just to say what the connecting topology is. So if B0 had no boundary, then this thing here reasonably will only have a boundary at 0. And then somehow it has an end at infinity that you're gluing this stuff to, and so the rest of the boundary should come from this. And the reason I didn't care about the boundary of the PSS ambient spaces is that they, these will have boundary by themselves, but they already sit in the boundary of this. So they'll just give you more corner stuff. So if we can make our polyfolds like this, I have a vague idea of what my Fredholm sections should be. Right? Namely, my section on the dense part that I've given there should better be my d-bar operator. Well, d-bar, I guess j hat 0 if I'm on B0, or d-bar j hat plus minus the PSS perturbed j's on the PSS spaces. And well, now it gets a little interesting, right? On this stretching polyfold I have two connected components. So on B stretch, I might either have a pair of a parameter and, well, some point in B0, so which might be a smooth point, that's just a U hat, well, actually an equivalence class, or something more complicated, like nodal structure on it. But that should simply go to the d-bar operator for the R stretch j of that U hat and whatever else, other components there might be. But there's also this part here, so I might have a pair of, well, either both smooth, simple non-nodal PSS and SSP solutions, or things with extra nodes and really the equivalence classes thereof. And so this pair should somehow go to the pair of the d-bars. And so one of the big mysteries is like, well, this is a 0-1 form over P1. This is a 0-1 form over C and another 0-1 form over C. So in what sense is that even somehow takes values in one and the same bundle over this space? So that's going to be sort of the guiding mystery in developing the notion of splicings. But for now, since we're just sort of topologically writing down maps, I can just say what I'd like my sections to be as maps on point sets, whether or not that's continuous or differentiable in some sense. So Fredholm is for the theory to well, describe in what sense it is. And so just on the level of topological spaces, again, I can just write the dense subsets for the spheres and for the plus minus PSS things. And that gets sort of guided by what I want my d-bar operator to be on those dense subsets. So I should have 0-1 forms here. Let's see. Oh boy, right, actually I need all U hats. And I need 0-1 forms over P1 of the pullback tangent bundle, P1 times n. That's usually where my d-bar operator takes values. And note that, so the polyfold itself didn't depend on this j hat. But this bundle will depend on j hat because I need to say in what sense they're 0, 1 forms. Right? So there's a little j on P1 and this capital J on P1 times m, and I'm asking for anti-holomorphic forms with respect to those two complex structures on those bundles. So the bundle changes because the operator changes. So here again I can play a similar game, just have all kinds of 0, 1 forms here. Those should be, dense subsets of that. I need to really worry about what happens when there's, nodal curves. And a similar worry then happens when I get to the stretching one. But here I can take, exactly the same bundle again. Except now, right, what should I do? So over this bit here, clearly, I want the product. Of those bundles, and the stretching thing, I want the fibers to be exactly the same fibers that I have over B0. So I just want this as extra parameter here. So I think this, strictly speaking, is a so from B stretch I have a projection to B0, and I should pull back the bundle over B0 to B stretch. And, ooh, that is now not good. Right. That exactly makes no sense because I prepared very carefully the fact that this bundle now depends on the j hat. Right, so that's wrong. What I should do is I should take union over all R and then take union of these bundles for different j hats. So that's going to sit over this. And then hopefully at infinity I can again topologize this by putting in those bundles. Problem is, as before, even like the fibers don't match. There's sort of a function space on P1 here, and there's 2 function spaces on C here. So there's even a jump kind of in the fibers of my bundle. It doesn't just look funky in the base. Which is actually a good thing. That's sort of one of the rules in this game is if something funky happens in the base, you better also have something funky happen in the fiber. And then there's sort of a cancelling of funkiness. So, these are all sort of very reasonable conditions on what my bundles and sections should be. Well, they're reasonable if I think of them in terms of cutting out the SFT moduli spaces. They're completely unreasonable if I wanted these to be Banach manifolds and traditional Fredholm sections. But that's exactly the goal, is to now change the language of Banach manifolds so that this becomes a reasonable expectation. All right. And now, actually, I'm going to simplify to the Gromov-Witten world. So, because we've actually talked about the Gromov-Witten setup, it's a lot less pesky in terms of what is the energy and what is the d-bar operator and what are my ambient spaces. But it's also, in that case, there's actually a theorem that's in the Gromov-Witten paper which is sort of true modulo a Dillon-Mumford paper, which at least I've seen the preprint of. So that theorem should now say that there is a polyfold Fredholm section that cuts out the Gromov-Witten moduli spaces. And we're going to restrict ourselves again to spherical spaces. So let's see. I would like and so oops. So there should be sections. So now we'll try to make this more rigorous, of the same polyfold but different bundles depending on the J. That's a compatible almost complex structure on my fixed symplectic ambient manifold. Right, so that the realization of the zero set should be my generalized compactified Gromov-Witten moduli spaces, and we, I think, usually label them by a homology class A, and I'd like the non-zero ones. So then all of these will be the Gromov compactifications of holomorphic spheres. Holomorphic spheres in homology class A. That by itself, right, if this is a well-defined homology class, this fixes the energy for me as something finite. I'm not going to put marked points on it, so I can just quotient by the whole automorphism group. So that's the sort of simplest spherical Gromov-Witten moduli spaces. If you actually want to do Gromov-Witten invariance, right, really you should put sort of a marked point on this, and then only quotient by things that fix that marked point. Which maybe I should have done. But that's all exercise translate, the minor changes in setup. So, right, so what are the main steps now of making this polyfold Fredholm description? So essentially they're sort of what I claimed in the very beginning of the course, is that there's always like I can describe my moduli spaces everywhere locally by some kind of Fredholm section. So, and that's what sort of gives me the structure on the object level. And clearly there's two important different cases, right? One is when you have just simply smooth curves, so that are in here. So this is my not yet compact moduli space. Then I need to think about nodal curves outside of that. And then I need to say what the morphisms are, right? Because I have different local Fredholm descriptions, so I need to somehow say, so what we're going to be able to say is how the Fredholm descriptions near different smooth curves are related. Then the relation to nodal curves is going to be a little more complicated. And at the end of the day, I would like my structure maps to somehow have decent smoothness properties. So that, in some sense, then the quotient I can think of as still having a smooth structure. So, let's see. Right. So, near a smooth curve. This is an exercise that we did, I think, in lecture 2. Right? So, I want to fix this action of the automorphism group, so I'm going to add 3 marked points to it. And I'm going to do this by picking a representative that's sort of nice and transverse at fixed points that I like. And I like in P1, I like 0, 1, and infinity. So I'm going to take d ZU to be injective at z equal to 0, 1, and infinity. Then I can make submanifolds HZ for each of these 3 points in M that intersect U transversely in those points. So, it should be transverse to the entire map, not just the image. So there's all kinds of technology involved here. If U is not globally injective, in particular, right, U at Z should be one of the intersection points. And if U was injective globally, I could make this the only point. But in general, U might be a multiply covered map, and so I'd have a bunch of intersection points. And it's just 0, 1, or infinity is one of the points that goes through there. So, right? And once I have that, I can make my Fredholm description. So that's so very generally, I should have a Banach bundle over a Banach manifold. And my base is now going to be called U because it's a smaller subset, right? And E is just going to be something small. So the main challenge here was to write down U. So that should be, a Banach manifold that's locally homeomorphic to this quotient space if I don't impose the d-bar operator. And so Banach, well, actually, I like Hilbert manifolds. And so from now on, everything is going to be Sobolev space with integrability 2, and those we often write H for. Right, so when I write H3, really what I mean is W K2, where K is 3. So when H3 maps from P1 to M, that I'd like to be pretty close to my center U. H3 here is because that makes them C1, right? And then if V is close enough to U, V is still going to be transverse to those hypersurfaces. And well, if it's close to that, then it also is going to have the same homology class, actually. And so all I need to then ask is that they satisfy the same slicing conditions. So I want V at Z in those hypersurfaces. So they'll intersect someplace near 0, 1, and infinity. I'm going to ask it to be exactly 0, 1, and infinity. So now you can convince yourself that that's a Banach manifold, which we'll actually do in a while. We're going to convince ourselves that it's a scale Banach manifold, which is more general. Well, so, right, so cut down the automorphism action by prescribing these intersection points. This is still a space on which I can perfectly easily write down my d-bar operator, and it's going to take values in all the 0, 1 forms. So I'm going to take the union over all the base points of the 0, 1 forms in the pullback tangent bundles. And that allows me to take the section to be the debar operator. That's, oops, out of the way. That is my section locally over this piece U. So that is now it's a Fredholm section, because that's something we know hopefully by now about Cauchy-Riemann operators. And so if there was no isotropy, then the zero set would give me an open subset in my zero set should give me an open subset in my moduli space, and so this here actually should be a homeomorphism. Except there might be isotropy, right? So in general there might be this quotient by a finite group. That's what we generally allow with our local Fredholm descriptions. And in this special case, that finite group is the stabilizer of my center map U. So that's sort of the general local slice theorem here. And then you just restrict your Fredholm section to that. So, mainly as a reminder of what our setting is, also as a structural reminder that when I say local Fredholm description, I mean Banach bundle, Banach manifold, a Fredholm section, so that the zero set, maybe modulo some morphisms, is locally holomorphic to an open subset of my modular space. And the challenge is to do something like that near nodal curves. So we're not going to do that today. That goes on our to-do list, maybe in purple, because that's going to get me into the notion of splicings. So instead, what we are going to do is we're going to look at the morphisms. So that's, I think, we're already, I've kept saying that we have a problem with the morphisms that has to do with non-differentiability of the reparametrization. And now is the time when we're really going to see that. So here you see, right, for every choice of smooth curve, you're choosing some small neighborhood. There's choices of hypersurfaces. Eventually, you're going to take your object space of your polyfold to be the disjoint union of all these U's. Right, so where you're taking enough of them so that all these footprints, so these open sets, actually cover your modular space. Right? But that, of course, will hit points way too often, so you're going to have to glue things together. And with that, once you know what these objects are, objects of E will then clearly be the disjoint union of all these E bundles E on U, and the section on object level will simply be all these sections here on the components U. So once you have the Fredholm descriptions, you're getting the object level of your categories and your sections for free. That determines them. So the morphisms, we have to make a decision here. we know what it should be on the level of holomorphic curves. And I'm just going to make the pretty reasonable decision now that, right, so in this case, at least, my non-holomorphic objects are also maps. And so I'm just going to use reparametrization, not just on the holomorphic maps, but also on the general maps. That's a fairly canonical choice here. I could have done something more funky if I wanted, but then I would probably burn in some other analytic help. So, right. I want to talk about the morphisms between two of these Fredholm descriptions. So, where source is in, one Fredholm description U, and the target is possibly in a different one U prime. Right, so one basic guiding example should now be if you take maybe even the same map, little u, the same domain, but you take slightly different hypersurfaces. Then what happens? So I should identify, right, a map with its reparametrization. So if I have a map in U and an automorphism of pi1, CP1, sorry, right, then I should identify that with the reparametrized phi. Right, so that would be my target of the morphism, and so it sits between U and U prime only if this is in U prime. Right. So what I'm doing here is I'm writing down the space of morphisms as a point set or topological set. And then as that set, the source map simply takes v comma phi to v, and the target map takes v comma phi to v composed with phi. Right? So really this is a morphism that identifies v and u with v composed with phi and u prime. So let's see. This here is still a Banach manifold. Namely, it locally looks just like U. Right, it's a submanifold of this bigger one. Right, this is 6 dimensions bigger from the Möbius transformations. But this condition here cuts the dimensions down by 6 again. Right, so this, if I give myself a V, odds are there's sort of a unique reparametrization that makes it satisfy the H prime slicing conditions. Or at best, there's sort of finitely many. So that gives us again a Banach manifold structure, right? And this is exactly the kind of game that I'd like, right? So object spaces and morphism spaces now have a smooth structure, and so then I can talk about my structure maps all being smooth. So structure maps here are already in place. Right? Every groupoid should have an identity, which here is sort of silly. So V object should go to the morphism, that's V and the identity. So that fits here. If I write U, then V composed with the identity is again V. You see how the stabilizer sits in here also, right? So if I have U comma phi that's in the stabilizer, so that U composed with phi is U. Right? So the pairs U with the stabilizer phis all sit in this morphism space here. that's why I didn't need them in the slices on the object level. So the ambiguity in my local slice also got pushed into the morphisms. And so far so good. Right, so now I also need to say what the composition is. Right, this is, well, I have something very specific in mind, so I can simply ask myself, when does this compose? Well, first of all, I can only compose this if the target is equal to the source. So the source here better be V composed with phi. And then if there's another automorphism psi, this should be like composing with psi at the end here, is that right? Oh boy. So this is certainly going from V to, so the target of this thing is going to be V composed with phi composed with psi, right? Okay. I hope this is the right order of composition here. I'm mildly confused because this is categorical order and this is order of composition. So I might have, written down a really weird group action here, which I might need to undo by writing phi inverse here. But let me not do that. So these are now all maps between Banach manifolds, so I could hope that they are all smooth. However, well, that looks about as smooth as it gets. This also, V goes to, it's a forgetful map, better be smooth. Here, really, there's sort of a forgetful map on a projection on the level of V, and then really you're just composing Möbius transformations, so that better be smooth. But here there's reparametrization going on, so this not so much. And so that's where our previous attempts at making a meaningful theory stopped. So what we're going to do instead is we're going to say that these are not smooth but scale smooth with respect to a scaled Banach manifold structure on this thing. And in that world also, all of these things will be scaled Banach manifolds and Banach bundles and scale smooth Fredholm sections. So, scale calculus is what gets invented in order to make sense of the morphism level of the construction. Yeah.
Should I think of scale like scaling things up and down, or scale like scales on a snake?
Oh goodness. You should think of scales as different scales of differentiability.
Okay.
So, and we'll get exactly there. So scales will be CK within C infinity compactifications. Sorry. You can compactify C infinity to Banach spaces in many different ways. In particular, there's a whole scales of Sobolev or Hilda compactifications. Yeah, it's a discrete scale.
Okay.
Somehow. It's not clear that that's the best name. It's also but part of that theory did exist previous, I think. It's just that the complete use of this for sort of differential geometry is new in Polyfold theory. Right. Oh yeah, and I just in terms of advertisement, right? So I said, so when we introduce nodal curves, we're going to need to introduce the notion of splicings, and when we're now pushing on morphism level to include the nodal curves, we're going to need to also say what sort of scale smooth maps between splicings are. So, but that's all gonna sort of come pretty much directly out of the conditions of what the theory should do. All right. So, now, so scale calculus you can sort of just define as the calculus in which the reparametrization map is smooth, and yet the rest of calculus still holds. So, to make that utterly precise, here's the simplest example I can think of. So, reparametrizing, right, I want to think of S1 as R mod Z. And then I can reparametrize functions. And I prefer that because now there's a very simple formula in which differentiation is also going to be very transparent. Little warning. Well, here it's important. It's kind of important to me that to show that the problem doesn't come from the group acting being non-compact. Right? So here the group that acts is S1, that's compact. At some point, so at some point I'm going to sort of misuse notation and declare this to be a vector space, which of course it isn't. But S1 locally is a vector space, namely R. So I'm gonna, but I didn't, and I could have written this as R acting on things, but then it would have been a non-compact group. Right? So I'm gonna be a little schizophrenic about that and not quite decide which one I want. But, right, so I want a smooth structure, a notion of smooth structure on this stuff, so that certainly that map is smooth. If I'm going to do any kind of analysis, I'd better have a chain rule. And if I'm going to cut out moduli spaces, I'd better have an implicit function theorem. And if that's supposed to have anything to do with, our traditional constructions of Gromov-Witten invariance, then the theory should somehow reduce to a known theory when I have transversality, which, in this case, I guess my implicit function theorem should somehow recover the sort of classical, or the whole thing, I guess, should recover the classical smooth structures when I'm on finite dimensional submanifolds of the smooth ones. So, well, let's see what we can do. So, I think there is a notion of Frechet differentiability in which this is actually smooth and it's even the chain rule holds, but there's no implicit function theorem. Because you'd like, Banach spaces to have, a Newton iteration. So, obvious idea is to take some Banach completions. And the reason I went to S1 is that good Banach completions here, we don't have to talk about Sobolev spaces, we could just take CK spaces. So, let me put ck everywhere in terms of, instead of c infinity. That will in fact be continuous for all k, starting with 0. It's sort of non-trivial to prove. So, if you write down your estimates, that you'll sweat at some point, and that sweat translates into not quite being able to prove differentiability from ck to ck, and we'll see what goes wrong in a moment. Let me just first claim that if I map from ck plus 1 to ck, I'll get differentiability. Namely, right, all I have to do is I have to write down what my, I have to write down my differential, and then I have to prove that that differential actually is a good linear approximation in the appropriate norms. So I should get to a bounded linear operator. So I'm going to write L for bounded linear operators. And that should now map from the tangent space of this to the tangent space of that. So that's R times C k plus 1 to C k. I'm going to try and indicate my scales in blue here. So the claim is that so first of all, right, these are bounded linear operators. And so let's see, what is a good guess, right? So I'm going to have to vary S in some direction, capital S, and the map little gamma in some direction, capital gamma. And if I do that on the right-hand side, well, right, if I add to little s and then differentiate by it, I'm picking up a derivative of gamma. So it's going to be a gamma dot, and that gets multiplied with, the real number s. And then when I vary gamma, that's beautifully linear, right? So if I fix S and I look at this map on the level of functions gamma, that's a linear map. So its derivative is simply itself, except we'll replace this by capital gamma. The nonlinearity is in the shift. So first check here. Let's see that the right-hand side even makes sense, right? So if gamma is in ck plus 1 and capital gamma is in ck plus 1, then this right-hand side, well, this guy is actually ck plus 1, that's great, but in order for gamma dot to be in ck, we needed gamma to be in ck plus 1. So that makes it pretty clear that there's no reasonable hope to have this differentiable from ck to ck, because the candidate differential doesn't even make sense. So, but you need, you'd actually, in order to check differentiability, you need to check now that this linear operator here actually, so secondly, you should check that that's a bounded linear operator, right? But we're allowed to do that for fixed S and gamma. And so that's linear in capital S because we're just multiplying by it, and it's linear in gamma because we fixed the shift. So looks bounded and pretty linear. So that exists differentiable, right? So here that you should, the one thing you should check is the sort of linear approximation. By that bounded linear operator. And what I want to claim in point 2 is also not only is this map well defined, it is actually continuous. For all k. So, meaning the operator norm here varies continuously with varying little s and little gamma. So in gamma, that's not so bad. If gamma varies continuously in ck plus 1, then gamma dot varies continuously in ck. When I vary s a little in s1, things get a little more complicated there. And that's going to create issues momentarily. So, yeah, I mean, that's a nice property. When you've shifted one, you get differentiability. The problem is that that really doesn't serve well for chain rules. You know, if you know compose things that are differentiable in this sense, you need to shift twice. Yeah. And you'd like to be able to say that if you compose two differentiable things, it's differentiable again. So, right, so let's see, right? So the first thing we've already seen, if I want to start at ck and go to ck, that totally doesn't make sense because it's not even well defined. Right, so this is not good. This is ill-defined. When gamma is ck, but not ck plus 1. So the next smart idea is to say, well, really nobody told me that I need, differentiability at all the ck things. Really, eventually I'm just interested in C infinity points. So maybe I just need to look at, smooth maps. And at smooth maps, this differential as a map from ck to ck should be, is well defined, right? So this map is well defined now. But is this continuous, right? And it turns out that it is not continuous. It's not continuous with respect to variations of S. And that is because of this pesky thing here. So one thing we should have is, right, so if as an operator norm this is bounded, you should be able to take a soup over all norm gamma equal to 1 things and look at a difference between gamma of s plus dot and gamma. And that, with s going to 0, that should go to 0. Let's go and look at k equal to 0. So just look at the C0 norm here. So if you give me a small s now that's non-zero, I'm going to make for you a function that has C0 norm 1, so it's bounded by 1, but within distance s jumps from +1 to -1. And if I shift this versus gamma, then oops, my C0 difference suddenly is 2. And I think 2 is the most you can do. but if I take, the problem is you first fix S and then you look at the soup. So the soup is always going to be 2. So it does not go to 0 as S goes to 0. This goes to 0 pointwise, right? If I fix a continuous gamma, then it has some uniform modulus of, continuity, and so it'll be fine. But it's not a uniform modulus of continuity for all the continuous maps. And that's a hint for how you prove this when you take, if I took gamma to be C1, right, then the bound on the first derivative of gamma would give me this uniform modulus of continuity that I'd need here to get continuity. So none of this is any good. However, right, there's this one little thing that's the pointwise. Pointwise, there's some decent theory. So this is the last thing that we can note here in terms of facts, is when I take ck plus 1 gammas, and then I act, right? So I want to take this statement here, but I'm going to take it pointwise. So from ck to ck. So pointwise, that is in fact going to be continuous. So that's the good news. And the even better news is, so now it looks like I have differentiability in some sense, and my, in some sense my differential is continuous. So maybe I have continuous differentiability. And in fact I can write this d tau in terms of taus again. So this is S times the shift of gamma dot with respect to S, and then the shift applied to capital gamma. So if I now have chain rules and reasonable definitions of differentiability and continuous differentiability, then I've written the differential in terms of things that themselves are continuously differentiable. So there's a hope that that means that actually tau was C2, and then I can bootstrap myself up to get smoothness. Except I now need a theory in which these couple of facts actually make up differentiability. So, and that's scale calculus. So I'm going to claim, well, I'm going to need to define scale smooth and scale Banach space, and then check that this map is actually scale smooth on the scale Banach space. So I'm going to use exactly the scales that I had there, namely the ck completions of C infinity for k bigger or equal to 0. So, and this is the definition of a scale Banach space, is essentially the list of nice properties that this scale has. So it's a little bit schizophrenic how I want to think about this. I really want to think of each of these scales not as a subset of C0 or as a different, I want to think of them as different completions. So I want to think of them as separate Banach spaces. Right? Each ck has its own ck norm. So that's the Banach spaces. I have injections whenever k is bigger than j. The natural map is in fact continuous, and because I'm on a compact domain, that's actually even a compact inclusion. So that's a good thing. And these are all completions of the same space, namely E infinity, the smooth functions, I get them now as intersections of all the scales. So that's your definition of scale Banach space right there. And with that, we can, completely formalize what the properties that I had before. So my property 0 was that on every, from CK to CK, I had continuity. So, I now need to look at a map between different spaces, and F, in my case now is, well, I'm going to write it as S1 times the CK spaces on S1. But really you should think of S1 as the Banach space R, right? So I want to talk about this, Tau is my shift map from S1 times C infinity to C infinity. And if I restricted it to a CK space, it was continuous from CK to CK. So if I'm a continuous map on each level, I'm something called scaled continuous. I'm scale differentiable if, so I needed these two things. If I shift by 1 in the domain, I get differentiable maps. And the derivatives make sense even when I shift in F back to CK. So this is saying that the derivative map actually makes sense as a map from, so there's a shifted product here, F1 times E, which is, what is it? Goodness, hold on. F1 times F, haha. So this is the scale structure that is Fk plus 1 in the base and Fk in the fiber. So that's similar to my Ck plus 1 times Ck, except with extra copies of S1 in between. And so, as this map is well defined, that was the observation that we had. And this is now sort of the pointwise differential. And what we saw here. So this is my Fk plus 1, this is my Fk to Ek, and as such this is continuous for all k, which means in our new world this is scale continuous. So, and now, that I have a derivative map, I'm just going to say that something is continuously differentiable if it is scale continuous, scale differentiable, and its hence defined derivative map is scale continuous. And finally, I'm going to call something scale smooth if it is, well, what do I need to say? I need to start here. Well, actually, I can just say if it is defined, so this here defines iteratively SCL, because I can, once I know what SC0 is, it defines what SC1 is. And then once I know what SC1 is, I know what SC2 is, and so on. And then I can say scale smooth if it's SCL for all L. And the previous list of facts is then exactly the proof that this reparametrization map is scale smooth. So that, of course, means now you can try and check the chain rule and all these fun things. And the one remark here is that apparently this compactness is crucial for the chain rule. I understand that in terms of I don't know how else to prove it. I don't know of a counterexample where the chain rule breaks down, you know, in an example where you fail to have compact inclusions. But that probably exists. So there seems to be sort of a pretty tightly defined, you know, theory. It exactly captures, you know, our conditions of, yeah. Right. So this is now scale smooth. Chain rule, well, you know, somebody has to work for that. Implicit function theorem, also somebody has to work for that. And next time I'm gonna start with explaining why this notion here exactly recovers the classical smooth structure. And then we have half of polyfold theory, well, a third maybe. Good. And this is now also a world in which somehow you can throw this at, you know, take some other reparametrization action and try to, you know, understand that this still, you know, structurally has exactly the same properties.